Hello everyone. In this lesson, we're going to be looking at how to find the sample size estimate for means based on some criteria that you would set. So when designing a statistical study, a good practice is first to decide in advance of doing the actual study what confidence level you want to achieve with this study, and also what is your maximum margin of error that you're willing to accept. So using these, we can calculate the required minimum sample size for calculating the mean based on some study that we're doing. So what we're actually going to do is we're going to start with our maximum margin of error, E equals Z critical sigma over square root of n. And what we want to do is we want to isolate n by itself to figure out what our minimum sample size is going to be. So first thing we're going to do, we're going to divide both sides by Z critical. And this is going to give us E over Z critical is equal to sigma over square root of n. Next thing we're going to do is we're actually going to cross multiply and then solve for that. So in other words, it's kind of the same thing as taking both sides and flipping them. So in this case, I'm going to put this to the left side. This is going to be the square root of n divided by sigma is equal to Z critical divided by E. Now what I'm going to do, I'm going to multiply both sides by sigma. And this is going to give me the square root of n is equal to Z critical sigma over E. And the last step we're going to do to get rid of the square root, we're going to square both sides. So the square and the square root will cancel. And I'm going to end up with n is equal to Z critical sigma over E all squared. And this is going to allow us to find our minimum sample size based on some critical value, right? Our Z critical, which is based on how confident we want to be, and our maximum margin of error that we're willing to accept for this study. Now, one thing I want to talk about before we move on actually showing how do we calculate this is oftentimes you're going to actually see me probably write it as n is greater than or equal to. And this is because, again, it's a minimum sample size. This means that having more is never going to hurt, right? So if I get a minimum sample size of 82 and someone says, well, I took 100 samples, you have more than enough. It just needs to be greater than that, greater than or equal to that 82. The next thing is, though, is what do you do if you get values that are a decimal? So in this case, what you're always going to do is you're always going to round up to the next whole value. So this means that if I get n is equal to 82.7, I would round this up to 83. If I get n is equal to 82.1, I would still round this up to 83. And in fact, if n is equal to 82, I still am going to round this up to 83. Now you might wonder, why do we always round up? Well, in this case, it makes sense, right? Because you're going to round to the nearest whole number. And it has to be a whole number because you can't have a decimal or fraction of a sample, right? If I'm saying I'm going to question 26.7 people, well, I can't have a 0.7 of a person. And also, because this is the minimum sample size, it means that it has to be more than or equal to that. And because I can't have 0.7 of a person, that means that I would need to go to the next whole person, or 83. This holds even for when it is below 0.5, right? Because it's not just round to the nearest whole number, it's round up to the nearest whole number. And the reason is because, again, if I have 82.1, I can't question 0.1 of a person. And if I go down to 82, I'm now below my minimum sample size, right? This is minimum, meaning that you can't be lower than this. The big one that causes a lot of confusion is why would we round up if we got a whole number like 82? And this actually has to do more with the limitations of our tools and making sure that we're being a little more conservative just to be sure. And this is because, like, for example, in this class, anytime we're doing any sort of calculation, like, for example, finding our Z critical, we're using a standard normal table. But every value on here is an approximation, right? Because we only have Z values that are to 2 decimal places. Any of our probabilities we find from the table are 4 decimal places, meaning that even if you somehow calculate a round number, you actually could be under calculating because of rounding error. So what we do is, just to be safe, we always round up. So if you had a minimum sample size of 82, it actually would be 83. In fact, when we're doing these problems, you're actually going to be getting two in values. You're going to get the minimum sample size calculated, and then you are also going to have the minimum sample size that you will use. Now let's do a couple examples to see how this works. The first example says, a child psychologist wants to estimate the mean age at which a child learns to talk. Find the sample size necessary for a 90% confidence level to ensure that the sample mean is within 5 weeks of the mean age at which a child learns to talk. Assume that sigma equals 10 weeks. So in this case, the information that we have is we want a confidence level of 0.90. We're assuming that sigma is equal to 10 weeks. And the next part of the problem, it states that we want to be within 5 weeks, right? Because we're dealing with the when children learn to talk based on number of weeks, this would be our maximum margin of error. So we want our maximum margin of error to be within 5. So now what we're going to do is we're going to find our minimum sample size. So our minimum sample size is going to be n is greater than or equal to z critical sigma over e, and then square the whole thing. Now we know what sigma is, we know what e is, we need to figure out what our z critical is. Now for a 0.90 confidence level, our z critical is going to be 1.645. So we have 1.645 times 10 divided by 5, and then we're going to take the whole thing and square it. And this is going to give us a value of 10.82. So our minimum sample size is we would need to go check on at least 10.82 children. But again, because we cannot check on a 0.82 of a child, this means that our n is actually going to be equal to 11. So we have a minimum sample size of 11. For the second example, we assume that the population data is normally distributed with a standard deviation of 1.4. Determine the minimum sample size required that when you want a 99%, you want to be 99% confident, so C equals 0.99, that the sample mean is within 2 units. So this is sort of just a generic problem where we don't know what this data actually represents, so we just want to be within 2 units of whatever it is, and it has a standard deviation of 1.4 units. So again, we're going to start by writing our minimum sample size, so our n has to be greater than or equal to z critical sigma over e, the whole thing squared. And then when we have a C of 0.99, this gives us a Z critical of 2.58. So we have 2.58 times 1.4 divided by 2. And then we're going to square the whole thing. And this is going to give us 3.26. Now again, we cannot use 0.26 of something, so what we need to do is we need to round up to the next whole number. So this is going to give us a minimum sample size of 4. Now, realistically, these problems are very simple cases. They're considered toy examples. So realistically, you probably would not want to have a minimum sample size of only 4, but this is just to kind of give you an example of how you would calculate this based on whatever it is that you're trying to find. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.